Okay, so we talk about graph search, how we can explore a graph. So before that, let us just finish the analysis of Prim's algorithm from the last class. So last class we have described the Prim's algorithm and we have taken an example how it is working. So now we will talk about the time complexity of this algorithm. So that is called analysis of Prim's algorithm. So as we know, Prim's algorithm is to find the minimum spanning tree. So input is a graph, we have a undirected graph V comma E, and we have a edge weight which is basically E. Each edge is associated with a weight. So the algorithm goes like this. So we assigned each vertex to a priority queue. So we put everything into the priority queue. We maintain this queue based on the degree of each vertex, and we assign the degree of each vertex is infinity, because this is the initialization, because initially nothing has been explored. So that is why we put degree to each vertex as infinity. So nothing has explored yet, but we have to have a starting vertex. So if you recall, the Prim's idea is a greedy choice. We start with the vertex S and we capture all the vertices which are connected with S to other vertices whose distance is whose edge weight is minimum. So that is the greedy option. So that is why Prim's algorithm is greedy choice. So we have to start with a vertex, and these vertexes we can choose arbitrarily. So for some arbitrary vertex S, we have to have a starting vertex, so that we can decide. So any vertex could be the starting vertex in Prim's algorithm. So that we have to choose arbitrary. And now this loop is for while Q is not empty, Q is starting with all V. Now we extract the minimum from this Q. Minimum is based on the key value. So initially minimum will be the S. So this will be the minimum. Initially S will be extracted and this will be U. And when we extract something from Q, it will be deleted from Q and it will be added in, say, what is a set called A set, say. So it will be deleted from Q, and then we check all the adjacency vertex of U. We check the whole adjacency vertex of U. Okay, and suppose these vertex are called V vertex. These vertex are called V vertex. So this is A complement, say. Now we check this V vertex if this is in Q. So if this is, so initially everybody has to be in Q, because initially U is basically S, other than U everybody is in Q. So their degree was infinity. Now we have to change the degree by this weight W of U comma V, because this was infinity, and in the later stage this is U. So we check the degree of this and we change the degree. So this is the relaxation. So this step is called, so we check the degree. If the degree is this step is called decrease key operation. Okay, and this step is called relaxation step. No, not relaxation. This is called decrease key operation. Okay, so basically we are this is not relaxation. This is the decrease key operation. So basically we are decreasing the key like this. So because these are having a degree which is more than the degree what we have the edge weight what we have right now. So we have to update that. So we update that and we will put a, so for who is the responsible for this update? This guy. So we put a link to that to have the minimum spanning tree at the end. And now again we extract the minimum. So that minimum will be the minimum among the bridge edge. So this is our A set. A set means everything in A is basically A complement is Q. A is basically Q complement. Okay. Now there is a theorem we have proved in the last class that all the bridge edges, if we consider A to A complement, whichever is the minimum has to be in this minimum spanning tree, and that will reflect in their degree. Okay. Okay, now talk about time complexity of this algorithm. So, the time complexity of this algorithm. So, this initialization step is for order of, so this is basically order of v times, v is the degree of the vertices. So, we can just write order of v. Actually, this should be order of cardinality of v, but anyway we are just denoting this v means the anyway, to be very specific we have to have this, and this outer loop is also order of, this inner loop is v times by this initialization step, and this outer loop while q is empty, because q is initialized by v. So, this is also v times. Okay. So, v times we are doing the extract minimum from the q. So, it depends how much time our q is taking to extract minimum. So, depends which data structure we are using for the q. We will come to that analysis. Now, this step, the inner loop is for this, for each of these we have to going for the adjacency list of u. So, this step will take, adjacency list of u. So, this we are doing for all v. So, this is basically summation of this, is called degree of, the cardinality of this is basically degree of u. So, this step will be take summation of the degree of u, u belongs to v. So, this is basically we know this is basically order of E by handshaking lemma, summation of degree is order of E. So, this time we are doing the decrease key, again decrease key will depend on the data structure we are using to have this. So, what is the total time complexity? Time complexity is order of v plus order of v times extract mean plus order of E times decrease key. So, the time complexity for Prim's algorithm is basically so the time for Prim's algorithm is order of, so it is basically v, order of v times time to extract the mean. So, it depends how we extract the mean, time for extract the mean plus E times time for the decrease key operation, because we are decreasing the key value of a node. So, we have to go to that particular node and we have to decrease this. Now, depending on so this is the order, we must write this as order form. Okay. So, this is the time complexity for Prim's algorithm in general. Okay. Now, suppose we depending on which data structure we are using to have this q, suppose we are using array for our q, suppose we are using array data structure, simple array, unordered array. So, that means we are putting everything, suppose our v is say, our vertex is say v1, v2, vn, suppose there are n vertices. So, we have a array, so v array is 1 to up to n. So, this is basically vn, v1 like this. So, simple unordered array. Okay. So, this is our q say. So, we are having a array for our priority queue. So, each of these element are q, this is the key value. So, this is the key value, each is initialized by except some value s, s is say vk. So, this is say k, so this is say vk. So, vk is basically s say, vk is basically s starting vertex. So, except this everything is infinity. Okay. Now, this is changing because this is the every time we are checking. So, we are extracting mean. So, how much time will take them find the minimum from this array? So, minimum extract mean will take. So, extract mean will take how much time? Because this is unordered array. So, we have to scan all the element. So, this is basically order of v times. And now decrease key. So, decrease key means suppose we have to decrease this value. So, this is the ith. So, we have to go to this position, we have to change. So, decrease key will take constant time. So, decrease key will take constant time, because we are going to that particular position of the particular position, and we are changing the value. Okay. So, in that case what is the time complexity? So, this is basically order of V and this is order of 1. So, this for array, this time is basically order of V square. For array implementation, time is order of V square plus E. I mean, this is the cardinality basically. Now, we know this order of E is bounded by order of V square. So, this is basically order of V square. So, order of n square if there are n vertex in this array in this graph. Okay. Now, suppose we are using a priority, we are using a queue, a heap, mean heap for this priority queue, mean heap. We know the max heap. Similarly, mean heap is basically the heap. We know heap is a data structure which is basically an array which is viewed as a binary tree. So, it is a array, ith element, note if ith element, then the childs are 2i 2i plus 1. So, that way we view the heap. So, for heap, if we use heap for this priority queue, mean heap, for mean heap, minimum is there in the root. So, for mean heap property is every node is less than from its child. So, that is the property of mean heap. Okay. So, if we use heap data structure for this queue, priority queue, mean heap particularly, then what is the time for extract mean? So, extract mean means we know the for mean heap, mean is in the root. So, for mean heap we know, this is the minimum if it is mean heap. Now, we need to extract this. To extract this, we can change with the last element here, and that will destroy the heapify property. Here mean heapify property, then we have to make it a heapify again. So, that will take log n time. So, it is basically order of log of V. Okay. So, that is the extract mean. Now, what about the decrease key? Decrease key means suppose we are going to decrease this key value. So, this having a value. Now, suppose it got decreased due to the algorithm, the whatever value it was having is more than the direct link from that u to that vertex. Okay. So, this has to be changed. So, if we change that, then it may violate the mean heap property. So, we may have to call mean heapify here. So, that will again take order of log n, because we do not know the position. So, order of log n. So, both the operation decrease key and extract mean will take order of log V. So, that means if we add these two time complexity here. So, for mean heap it will take time is basically so order of log V and order of E log V. So, basically it is order of E log V. This is if we use the heap implementation, heap as a priority queue. Okay. So, now there is another data structure which is called Fibonacci heap. So, let us write this in terms of, so priority queue T extract, we will write this in a table, extract minimum time and then T decrease key, and this is the total time. Suppose we are writing this in a table. Okay. Now, suppose this we are using an array for this priority queue. So, with the data structure we are using here. So, this will take order of V, this will take order of 1, this will take order of V square. So, cardinality of V square basically. Okay. And if we take the binary heap, that means in particularly mean heap, Then we have seen this will take order of log v, this will also take order of log v, and this will take then order of E log v. Okay. Now, if you take another data structure which is called Fibonacci heap, so this is there in the textbook, Fibonacci heap, then we can show this will take order of log v amortize. So, this analysis is amortize analysis. And this will take order of 1. So, this is also amortize. So, the total will be order of v. So, order of v into log v, and order of 1 means decrease key. So, this is E. So, there basically it will take E plus v log v. So, total time complexity is E plus v log v. So, this is the best among these. So, this is also worst case amortize analysis. So, this is the best data structure for this analysis. Okay. So, this is the analysis of Prim's algorithm. So, basically depending on the data structure. So, if we use the Fibonacci heap, the amortized cost in the worst case is order of E plus v log v. So, this is the best we know, okay, for the Prim's algorithm. Okay. So, now we will start the next topic. So, this is the Prim's algorithm time complexity. So, this time complexity will be same as when we will talk about Dijkstra's algorithm for finding the shortest path. So, just to there we will not discuss this whole details. So, you have to recap, you have to come back here to have the analysis for analysis this table. Okay. So, let us start with the new topic which is called graph search. So, how we can explore a graph. So, this is called basically graph search. So, this is to basically explore a graph. Explore a graph. So, what do you mean by exploring a graph? So, that means suppose we have a vertex A, source vertex, and we have another vertex T. We want to find a path from S to T. So, that is one way of exploring a graph. Maybe we want to find all the path from S to T. We want to find all the path from S to T. So, this is one way to explore a graph. Okay. Or maybe we want to find the shortest path from S to T. We want to find the shortest path will come with the weight. We may not have weight there in a graph. So, this is a given graph. We have a graph. We want to explore it. So, this is one way we can find out the path from a source vertex to another vertex. We may need to find out all the paths from source vertex to another vertex. So, we will talk about breadth first search. This is one way to exploring a graph. Breadth first search. This is in short called BFS. So, this is one way to exploring a graph. So, there are many applications of exploring a graph. So, let us just jot down some of the applications of. So, one application may be social network like Facebook. Okay. So, Facebook we can consider user as a node, and suppose I want to find my all the friends. So, we have to explore the graph. So, or suppose there is a friend, there is a node user, I want to see whether I have I can reach to that user through my friend. So, this is a one application. Another application is maybe garbage collection. So, so most of the operating system is having this garbage collector, like if we use some memory and if we no longer using that, suppose we use calloc or malloc, and then if we free that without freeing that, suppose we are no longer using, so it need to be free, so that other next time we can use this. So, that step we can do. So basically we have to see whether we can reach from this to that space. So, if we cannot reach, that means that is not using. So, that way we can, that is one applications. Then web cloning. So, if we have a data, if we have a new web page, I want to have a access from the other. So, Google has to access all the new web page. So, that is the also exploring a graph, and solving puzzle like Rubik cube, how we can solve the Rubik cube. So, I think I have a Rubik cube. Let us bring the Rubik cube. So, this is the Rubik cube, or this is called pocket cube. So, this one. So, solving this kind of Rubik cube. So, solving puzzle. Okay. So, that is these are the applications for this. So, let us start with the Rubik cube or the pocket cube, how this can be applied there. So, how we can associate this graph search with the pocket cube. Suppose we have this is a 3 cos 3 Rubik cube, but suppose we take the lower version. Suppose we have a 2 cos 2 pocket cube. Suppose we have a 2 cross 2 pocket cube, or this is the Rubik cube. Okay. So, how we can think this Rubik cube as a graph? We take each position as a graph, node of a graph, vertex. This is a position, we take node, this is a vertex. If we change one little, then it is another vertex like this. So, if we change this, this is another vertex. Okay. So, this is another vertex like this. So, each position, each state, this is one state, each state is a vertex of a graph, and suppose we are in solve state. Okay. Now, if we take just one move, then there will be another state. So, that is the basically, suppose we are at solve state. Solve state means all the colors are matching in a same, this is not solve one, but solve state means all the color are matched. That is also a state, that is also vertex of a graph. And at the solve state, if we just have one change, 90-degree change, okay, then that will be another state. Suppose these are the vertices which are basically one step. So, these are the basically one step away from the solve state. That means, from this we can have a one move to go to the solve state. So, from solve state we did one change to get this state. So, this is basically one step from solve state. Okay. Similarly, if from there we can have two move, another move. So, this is basically two step away from the solve state like this. Okay. So, this is maybe here. So, like this. So, this is the two step away from solve state. So, this way we will continue, we will reach here. Okay. So, this is the last state like this. So, this is called, this is an example of a breadth first search, breadth first tree basically. So, this tree is called breadth first tree, BFS. Okay. And you will be surprised to know this dimension, this is called dimension, or this is also called got number. This is basically 11 for 2 by 2 by 2 Rubik cube. Okay. So, now how many states are there in this Rubik cube 2 by 2 by 2? The number of vertices basically number of vertices are basically factorial 8 into 3 to the power 8. Okay. So, this many vertices we have. So, this many possible. So, this is huge number. This is basically 2, 6, 4, 5, 3, 9, 5, 2, 0. This is the number of state of this graph. Okay. But dimension is 11. You can, there is a proof that one can show the dimension is 11. This is called God number or the dimension of this. This is for 2 by 2 by 2 Rubik cube. Now, how to show this graph has this number of vertices is this. So, basically how to show this? I just try to have a 2 by 2 by 2 Rubik cube. Okay. Now, if we take this one state like this, one part of like this. So, basically what are the so there are basically 8 ways we can choose this. So, 8 ways means, so 8 are the possible that cube we have, this small cube. So, that means factorial 8 is the possible ways, and each way there are 8 dimensions and the 3 ways we can change that. So, this is basically 3 to the power 8. So, that is why it is this. Okay. So, this is the that breadth first search is basically this, the Rubik cube we just go from the opposite direction. From solved state we saw how to reach to the another state, the one step away, 2 step away like this. So, this is the, if we do the other way around, then that is called breadth first search. So, we will formally have the algorithm for breadth first search. So, that we will do in the next class. Thank you.